In this lecture, we're going to start our unit on Riemann integration. What we're going to do is integrate bounded functions over closed bounded intervals of the form a to b. So anytime you think about a function in this context, picture it as bounded, and the domain in question is this closed bounded interval from a to b. The first thing we're going to do is work with the domain. Then we'll bring in the function and talk about what it would mean to say that a function was integrable over the domain. So for our domain, we're looking at an interval of this form, the closed interval from a to b. What we ultimately want to do is come up with the concept of what it would mean to say the area sitting between the x-axis and the graph of some function. In order to create this notion of area, what we typically do is take the graph of our function and break it up into little rectangles, calculate the areas of all those rectangles and add them together. And this is the idea behind how we're going to set up Riemann integration in this advanced calculus course. The first thing we're going to do with our domain is define the notion of a partition. A partition is any way to finitely chop up the domain. So you don't imagine with a given partition that you're chopping forever. Rather, you think of yourself as making a finite number of cuts in the domain, which do not need to be evenly spaced. Sometimes when students learn about integration, you imagine that you've chopped up this domain from a to b in a uniform way so that all of the subintervals have the same width, but that's not what we're going to do. We'll designate the leftmost value a as the partition point x sub 0, and the rightmost value b is actually going to be x sub capital N, and then everything between goes through x1 through x sub capital N minus 1. So this, in this picture, I would have x1, x2. Let's imagine that I'm kind of skipping over possible points. Let's call this xi minus 1, xi, like this. It's important here that your subscripts are always set up the same way so that the first subscript is 0 and the final subscript is capital N. Then if you look at this very first kind of subinterval that we've created, it's the first subinterval, and the number on the right, the subscript on the right, is 1. So from the left side to the right side, you index your subintervals using the right subscript. Therefore, this subinterval is the ith subinterval, and we can say that we have n total subintervals. The width of this ith subinterval would be the right point minus the left point. That's just width of this interval. And we denote it with the Greek letter capital delta. So what we'll say is that the ith subinterval width, which we'll actually denote like this, delta xi, is the positive number xi minus 1. So any partition of the closed bounded interval from a to b is just a way to chop up that interval. We can think of it as the set of points which define all of the subintervals. So mentally you picture kind of a chopped up domain, but technically a partition is the set of points. So here we have n plus 1 total points. You always have a finite number, so you could have a partition with just 2 points consisting of the n points only. So you just have the one subinterval going all the way from a to b. You could have 3 points, which would give you 2 subintervals from a to some central point, and from that central point to b. You could have 1,000 points, etc. But you don't want to imagine a partition as kind of increasingly chopped up. So whenever you think of a partition, think of a finite chopping up of the domain from a to b. Now imagine that we have any bounded function over this domain from a to b. A couple of remarks to make here. Even if the book says continuous, it doesn't need to be continuous. All you have to picture is a bounded function. And moreover, your function is defined for every number between a and b. So when we say it's a function on a to b, we mean that it is a function defined for every value in this closed bounded interval. For example, we would not be considering something like 1 over x from 0 to 1 or something like that, a because it's not bounded, and b it's not defined on 0. Given some partition P, think about the ith subinterval. So that goes from the partition point x sub I minus 1 through xi. Since we are assuming that we have a bounded function, the supremum property tells us that since it's bounded above, it has a supremum. Since it's bounded below, it has an infimum. So it makes sense to define these numbers. Little m sub I is going to be the infimum of all of the outputs that f takes over the ith subinterval. And similarly, capital M sub I is going to be the supremum of all of the output values over the ith subinterval. If it happened that our function were continuous over the ith subinterval, we could actually call this a minimum and a maximum, but we don't know that that's necessarily happening, so we might not have an actual continuous function. Given our partition, we define two types of sums of f, is what we call them. The lower sum of f with respect to the given partition P is going to be the sum. It's going to index across the subintervals. So from I equals 1, that's going to refer to the first subinterval, through I equals capital N, that's going to be our last subinterval. It's the product of the infimum of the given subinterval times what is ultimately the width of the subinterval. So if you like, we could write this as the sum from I equals 1 through N of the lower bound of the set of outputs times the width of each interval. You can think of that lower bound as like a height. Since it's the infimum of the set of outputs, it's going to be like the tallest height that sits under the function. Then delta xi is the width of the given subinterval, so this is really like adding up a bunch of areas. Here's what it looks like for a given function. So this app has more going on than what I'm picturing, so it will also show us the upper sum and things like that. But here I've got a random partition with 5 subintervals. So as you can see, my partition is not evenly spaced. Here's a really wide subinterval. You can barely see this very skinny one right here. And what we're looking at is the lower sum of this bounded function, that's this black curve at the top, this bounded function with respect to this partition. So if you look at this first rectangle, the infimum of f is actually being given by this left value over here. So this is the infimum of all the set of outputs that f takes over this first subinterval. So what we would be adding up to get this lower sum, which is about 5.0141, would be the width of the subinterval times the height of that infimum value. Then our second subinterval is really wide, and then here, about right over x equals 3, we see how to determine the infimum of all of the set of outputs that f takes over this second block. And then the third one, the infimum is here, fourth one, fifth one. So with respect to this partition, the sum of the areas of these 5 rectangles would be the lower sum of f. I can show you a few others. Here's another partition with 5 subintervals. Again, pictured as the lower sum of f with respect to this partition. Here's some more lower sums, all with 5 subintervals. Let me increase the number of subintervals to 10. So here are 10 subintervals forming a partition with 11 points. And pictured are rectangles formed by taking the infimum of all of the outputs that f takes over each subinterval. Similarly, we can define the upper sum of f with respect to a given partition. This would be adding up a bunch of areas where the height is now being determined by the supremum value, so that's going to sit over the function. Now we're going to be looking at rectangles which are quite tall, so let me take away the lower area and show the upper area. Here's a partition with 10 subintervals, and as you can see, over each subinterval, this program figures out the supremum value and creates the corresponding rectangle whose width is the given subinterval and whose height is that supremum value. Let me shrink down to say 5 subintervals. If you've been paying attention to these numbers, you'll notice that the upper sum is always larger than the lower sum with respect to each partition. If I picture both of them, it's clear why that would be true, because the supremum is greater than or equal to the infimum, and then the widths are the same. So what we have here is that this number is greater than or equal to 0. The widths are each positive. So overall, the upper sum minus the lower sum of f with respect to a given partition is greater than or equal to 0. Here in the second one, you can see that this subinterval is so narrow that the supremum and the infimum are really, really close together. But of course, for a given partition, they might be quite different. In the back of our minds, what we know we're setting up is the notion of area under the curve. So what you could now say is the upper sum is an overestimate, the lower sum is a lower estimate. It's important to realize that unlike in a calculus class, not only is our partition not necessarily evenly spaced, so here I have a wide subinterval, here I have some narrow subintervals, but also we're not picking something like the left endpoint or the right endpoint or the midpoint of each subinterval, which is often the algorithm used to compute integrals by hand. What we're doing is I don't necessarily know where the supremum or infimum of a subinterval occurs. So to pick our height, instead of trying to specify a point from the domain, we're just actually specifying a height. Pick a tall height or pick a short height. Given a partition P, if we take all of the points which currently exist in P and then we add a few more, so we chop up our domain a little bit more, then we call the new partition a refinement of P. So we say that Q is a refinement of P if Q contains all of the points of P and maybe more. So if these points currently pictured are the points of P, and then I add in a few more, then what we're doing is refining our partition. So let's think about what would happen to the lower and upper sums of a function over, say, a partition P versus its refinement Q. Our result is going to be that if Q refines P, so this notation means all of the points of P are contained in Q, but maybe Q has more points, then the lower sum of Q is greater than the lower sum of P. So mentally what you picture is something like this. Here is a lower sum of our bounded function over 5 subintervals. Let's look at this wide middle subinterval. Notice its infimum is happening right around x equals 3. If I took this partition and I refined it by, say, adding the point 2 to the partition so that we would now have 6 subintervals, then this subinterval I would be creating from 1 to 2 would have an infimum which is much higher than the height that we currently have for this wide middle infimum, right? So if I dropped in and kind of created a new subinterval where I'm moving my mouse, the height would go up, which would mean that we would be adding more area, right? So if we can make our partition finer, then some of these heights are going to increase, and so we're going to be having more area. That's why we say that the lower sum of a refinement is larger than the lower sum of the original partition. Similarly, if I have the same partition now, but I'm looking at the upper area, and again I refined this middle subinterval, then this very tall height is going to go down. Like say now I'm looking at 2 to 3.6 or whatever this set, like kind of right half of this subinterval is. Over that subinterval that I would be creating with my refinement, the height would come down because the supremum would likely be lowered. So as you refine a partition, your supremums are going to be chosen a little bit more carefully for smaller and smaller subintervals, which means that these heights would come down. Therefore, I would be adding less area together. So the upper sum of f over the refinement is actually going to be less area than the upper sum of f over the original partition. So our upper sums will go down as we refine. So lower sums go up and upper sums go down. Since partitions only consist of a finite number of points, to get from P to its refinement Q, I could imagine adding 1 point at a time. Like let's say Q has 23 more points than P. I could just add each of those points one by one, and if I could show that each time I added a point, the lower sum and upper sum changed according to this lemma, then that would be done. So in other words, all we have to do is imagine taking a partition P and refining it by adding in one more point So let's suppose that Q refines P by adding a single new point to it, which I'll denote by x tilde. So in particular, suppose that the kth subinterval is the one that gets affected, and we're going to take the kth subinterval in P and split it into two subintervals, maybe not equal width, but we're just going to drop a point in between xk minus 1 and xk to get the two subintervals xk minus 1 through x tilde and x tilde through xk. Now what I want to do is add up the lower sum of f with respect to q. So first let me bring in our notation for infimum. Let m sub I, this is little m sub I, be the infimum of f of x if x lives inside of one of these original subintervals from P. So this is not going to work for our two new subintervals, but for all of the other subintervals, we're going to have identical notation that we would have as if we were computing the lower sum of f with respect to the original partition P. Then what does the lower sum of f with respect to q looks like? Well, let's imagine that this first vertical blue bar is the one that gets added. So the lower sum of f with respect to q doesn't change to the left of the affected partition. So let's bring in this sum. So this is going to go from the first subinterval through the k minus 1 subinterval. That's all of the subintervals to the left of the affected subinterval. Then it's little m sub I times the original width. Now my subinterval got split into two, so we've got to compute the infimum of f over this new subinterval from k minus xk minus 1 through x tilde. That looks like this. So we have the infimum of our set of outputs over this new created subinterval times the width of that subinterval. Plus, same story but for the second newly created subinterval, so the infimum of the set of outputs where x is between the new point x tilde and xk times the width of that subinterval. And then to the right, we're good to go. So we just do our original infimums and original widths. Now I'm going to make a small change. For this first infimum calculation that we have, let me increase the size of the domain. The greatest lower bound, if anything, could shrink. So instead of going from xk minus 1 through x tilde for this first kind of manual calculation, let's go from xk minus 1 through xk. Because we're bringing in more output values, the greatest lower bound, if anything, it goes down. Same story for the second calculation. I'm going to take this domain and start it at xk minus 1 rather than x tilde because we're bringing in more outputs. If anything, the greatest lower bound goes down. Everything else is the same. And now we see that this term right here is really m sub k, and so is the second one. If I factor little m sub k out of these two terms now, I would get m sub k times the length of the newly created left interval plus the length of the newly created right interval, which is the length of the original intervals. So now this new expression is exactly equal to, after simplification, the original lower sum of f with respect to the partition P. The result for upper sums is found in a similar manner. So as we just saw, as you refine a partition, your lower sums go up. As you refine a partition, your upper sums go down. The next lemma tells us that an upper sum and a lower sum never cross each other. All lower sums of f with respect to all possible partitions are always under every possible upper sum. So here, imagine P and Q are any two partitions at all. They don't have to look anything like each other. They don't have to be refinements of each other. They're just both random partitions of our domain. No matter what they look like, the lower sum of f with respect to P has to be under the upper sum of f with respect to Q. So a lower sum can never be larger than an upper sum, no matter how you choose your partitions. The proof is actually easy. Let's let capital R be the common refinement of both of them. So it's like I'm going to take all of the points that form P and join them with all of the points that form Q. So now we have R refines P and R refines Q. Based on our previous lemma, we can say that the lower sum of f with respect to P is less than or equal to the lower sum of f with respect to R because R refines P. But when we set up lower and upper sums, we set a lower sum of f with respect to a given partition R is smaller than the upper sum of f with respect to the same partition R. So I can say that the lower sum of f with respect to R is less than or equal to the upper sum of f with respect to R. But now R is also a refinement of Q. And as you refine, your upper sums go down. So the upper sum of f with respect to R is less than or equal to the upper sum of f with respect to Q. And now the leftmost term and the rightmost term give us what we want. Given a closed bounded interval from A to B, there are uncountably many ways to write down a partition. So you could never ever write down every partition of a given domain, but somehow consider the collection of all of them. So just imagine that we were taking into account every possible way to create a partition of a given domain from A to B. We define what's called the upper integral of a function f to be the infimum of all of the possible upper sums that you could come up with. Similarly, the lower integral of f is the biggest lower sum across all possible partitions. Since all upper sums are bounded below by every single lower sum from the limit at the top, this infimum does exist because we're bounded below, so a greatest lower bound. Similarly, all lower sums are bounded above by any given upper sum. Therefore, the set of all lower sums is bounded above. So by the supremum property, there is a least upper bound. So we can define a supremum. At the top of the page, we said that all upper sums of f with respect to any partition are greater than or equal to all lower sums of f with respect to any partition. Our new claim is that the upper integral of f is greater than or equal to the lower integral of f. This proof is not too hard. Let's set up contradiction. So imagine that the upper integral were actually less than the lower integral. If the upper integral is less than the lower integral, then what I can do is think of the distance between them as a positive number, which I divide into thirds. Then by the characterization of a supremum, I can find a lower sum which lives in this closed interval whose right endpoint is L of f. And using the characterization of the supremum but for an infimum, I can find an upper sum which would live in this closed interval for which U of f is the left endpoint. And that's a contradiction. So here's the proof. For the sake of contradiction, suppose that U of f is actually to the left of L of f. Then through that characterization, there must be partitions P and Q, so that the lower sum of f with respect to P would live in this closed bounded interval whose left endpoint is L of f minus L of f minus U of f, that's the distance between them, divided by 3, through L of f. So that puts the lower sum of f with respect to P in this interval. Meanwhile, the upper sum of f with respect to Q would be found in this interval. And then that contradicts the lemma that we proved at the top of the slide. Now we're ready to define what it means to say that a bounded function over this domain from A to B is Riemann integrable. We just saw that the upper integral of f is always greater than or equal to the lower integral because all upper sums are greater than or equal to all lower sums. If it turns out that those upper sums kind of come down and meet the lower sums, then our upper integral will be equal to our lower integral. Then we can say that f has like a true area under the curve, and that's how we define the Riemann integral. So you could say the integral of f from A to B is the upper integral of f, or equivalently, the lower integral of f, since those two numbers are the same for a Riemann integrable function. So in this bounded, not continuous function I have over the domain from 0 to 4, if I just look at partitions with 10 subintervals, you can see my upper sum is always bigger than my lower sum, as expected. And they're pretty far apart. So just looking at those numbers, they're consistently about 3 units apart. But when we talk about upper integrals and lower integrals, we have to look at all possible partitions. So we have to imagine that we also considered partitions that had 50 points. And now you can see they're starting to come a little bit closer together. So this upper sum of f with respect to this partition is 9.3542, and the lower sum is 8.54. If I try another one with 50 points, You can see they're still somewhat far apart, in particular where we've got these jumps, but they're closer together. Let me try a partition with 100 points. And we're doing a little bit better, so we've gone from about 3 units apart to about half a unit apart. This is a little bit better. This one's pretty good. You can see that we have a big difference right here on this first jump point, but imagine taking this partition and now chopping this block up into 100 subintervals. So take this very partition, refine this one in the middle, refine some of these over on the right side a little more, and these two numbers are going to get closer and closer together. So this function pictured over the interval from 0 to 4 is a Riemann integrable function. I can't remember exactly what its area is, but it would be between these two numbers, so let's guesstimate about 8.9. The main drawback of the definition of Riemann integrability is that it involves these quantities, the upper integral of f and the lower integral of f, and then each of those is a number which must be computed with respect to all possible partitions, which you could never describe, you could never enumerate. So we would like to have other ways to show that a function is integrable without needing to take into account every possible partition. So one of the most useful techniques is to use something I call the criterion for integrability. The criterion for integrability allows us to say that a bounded function f is integrable from a to b if and only if, for every positive number epsilon, there exists a partition p sub epsilon, so that the upper sum of f with respect to p epsilon minus the lower sum of f with respect to p epsilon is less than or equal to epsilon. One thing I would point out is the number on the left-hand side right here is greater than or equal to 0. We already proved that. But if you want to, you can put absolute values around that quantity just to make it look like the type of estimate that we typically show in advanced calculus. So we're trying to show that the distance between the upper sum of f with respect to this partition and the lower sum is as small as we want it to be. Couple remarks, this is an if and only if proof, so we're going to prove both directions. Second remark is that in the latter clause, first you pick epsilon, then you know that there exists a partition. So you have to first choose how close you want those two quantities to be, and then if you can show that there is a partition, you know your function is integrable. For the proof, the backwards direction is actually easier. So suppose that given any choice of epsilon greater than 0, we know that there exists some good partition of our domain so that the difference between the upper sum and the lower sum is less than or equal to epsilon. So let epsilon be greater than 0 and choose that partition accordingly. Now notice that the distance between the upper integral and the lower integral, well actually I don't need absolute values here because we know u of f is always greater than or equal to L of f, so let's go ahead and take off those absolute values. The upper integral u of f is the infimum of the set of all upper sums. So u of f is a lower bound to all possible upper sums, which means u of f is less than or equal to the upper sum of f with respect to p epsilon. Similarly, L of f is a supremum of the set of all lower sums, which means here I'm taking off a larger number than if I only took off the lower sum of f with respect to p epsilon. But now I've got the upper sum of f with respect to p epsilon minus the lower sum, and that by assumption is less than or equal to epsilon. Since epsilon is as small as we want it to be, we conclude that the upper integral must be equal to the lower integral, and therefore f is Riemann integrable. The forwards direction is actually harder, even though with the forwards direction we have the very strong hypothesis that f is integrable. So given that f is integrable, I need to show you that there exists an actual specific partition, which we'll name p sub epsilon, so that this holds. It's a little bit harder because we actually have to tell you how to design this partition. So for this backwards direction, we're going to suppose that f is already known to be Riemann integrable on a to b. In other words, its upper integral u of f is equal to its lower integral L of f, and let epsilon be any arbitrary positive number. For this proof, it's going to help to have this little diagram here. So remember, lower sums sit to the left, upper sums sit to the right, and because our function is Riemann integrable, we're assuming that they kind of meet in the middle where L of f, the lower integral, is the supremum of the set of all lower sums, and it's equal to U of f, the upper integral, which is the infimum of all upper sums. So when you're working with this notation, sketching this little picture can help. By that famous characterization for a supremum that we've used many times, we know that if I take this infimum U of f and I go a little bit to the right and consider the closed interval from U to f to U of f plus epsilon over 2, there must be an element from the set of all upper sums which lives in this closed bounded interval. In other words, we must have an upper sum which lives in here. So by the characterization for a supremum, there exists some partition which I'm going to denote p sub 1, so that the upper sum of f with respect to p sub 1 sits inside of this interval from u of f to u of f plus epsilon over 2. Similarly, we can go the other direction. So if I go to the lower integral and subtract off epsilon over 2, I know that in this region I'm going to have a lower sum. Therefore, there exists some other partition. It's probably not the same partition as p sub 1, so that's key. There exists some partition, let's call it p sub 2, so that the lower sum of f with respect to p sub 2 lives in the closed interval from L of f minus epsilon over 2 through L of f. We have two partitions and we're trying to get to one good partition. So let's take the common refinement. The partition that we want to name for our criterion for integrability is this p sub epsilon, and let's have it be the common refinement of these two partitions we've identified, p1 and p2. Now we need to show that the upper sum of f with respect to p epsilon minus the lower sum of f with respect to p epsilon is less than or equal to epsilon, but this is not too hard now because of what we've set up. So let's compute this number. Notice p epsilon is a refinement of p1. Therefore, if I go from the refinement back to the original, my upper sum is going to increase. Similarly, the lower sum of f with respect to p epsilon is greater than or equal to the lower sum of f with respect to p2 because p epsilon is a refinement of p2. Therefore, on the left-hand side, I'm subtracting off a larger number than I would be subtracting off on the right-hand side. So we get this inequality. Now, u of f with respect to p1 sits inside of this interval right here, which means it's less than or equal to u of f plus epsilon over 2. Similarly, L of f with respect to p2 sits inside of this interval, so negative L of f with respect to p2 is less than or equal to negative L of f minus epsilon over 2. Right, so you just imagine taking this interval and flipping it. Now we collect like terms. U of f minus L of f is actually 0 because our hypothesis is that those two numbers are the same. And so what we're left with is epsilon over 2 plus epsilon over 2, which is epsilon. Now we've proved both directions for the criterion for integrability, which means we can use it. And what's really nice here is that sometimes in order to prove that a function is integrable, it's actually not that bad to construct a partition or to give a way of constructing this type of partition so that the upper sum minus the lower sum is less than or equal to any arbitrary epsilon. That can be easier than showing that the supremum of all lower sums must be equal to the infimum of all upper sums.